Okay, so the principle of conservation of energy just says that energy is conserved. And so if you add up the total energy before in a situation, it's going to equal the total energy afterwards. Another way to say it is that the energy comes from someplace and it goes someplace, right? Some people like to think about money, right? You know, we spend money, right? So what we have, we spend. Ultimately, though, for our purposes, it's going to be just this notion here, right? That we've got, these are, and all I've done here is I've added up all the formulas that we have for energy, okay? So this is work, this is potential, this is kinetic, that's a spring right here, okay? And what we do is we look at the problem. So like, for example, we might have some kind of a thing like this, and a little object might slide. Maybe that's frictionless, or maybe there's friction or something like that, right? Okay, I'll put wheels on it like that, right? Okay, so here this thing is, we could exert a force over a distance, right? So we could speed the thing up. And this is, you should write this down because work is actually a tricky thing, right? Okay, work that speeds you up is an asset, okay? Okay, so that's going to be force this way, and the velocity would be in the same direction. Okay, so maybe we speed the thing up. It's definitely on the top of a hill here, right? So we've got some height, right? So we definitely have potential energy. Maybe before we sped it up, it was already moving, right? So it had a little bit of kinetic energy. I can't think of a way to get a spring into this problem, right? And then as expenditures go, right, if work is an expenditure of energy, it has to be a force that slows you. Okay, so as you look at these problems and you try to figure out where the force times distance is, you're going to look at whether it speeds you up. If it speeds you up, it's an asset, and if it slows you down, it's an expenditure, right? Okay, so for slowing you down, of course, if the velocity is this way, the force is opposite that somehow, right? And then at the bottom of this hill, it might just be that there's no potential. Maybe there's no force that they talk about slowing you down. Maybe there is, right? But definitely, maybe it's moving at the bottom of the hill, right? So rather than talk about a problem that we might solve, let's just actually solve a problem here. Okay. So here's this cart. It's a 250 kilogram cart. It's going 4.5 meters per second before it even gets to the hill, and then it rolls down a 1.75 meter tall hill, and we don't even need to know how long that ramp is. Okay. What is the velocity of the cart at the bottom? Now, by the way, before this, we would have to actually figure out the degree of incline, figure out the parallel component, mg sine theta. We'd have to figure out the acceleration. Then we'd have to figure out suvat, with this as the initial velocity. Energy is much simpler, even though maybe right now it doesn't look simpler, right? So let's look at all the things that we have, right? In these words here, do you see any mention of any forces acting over any distances? Okay, that's a question mark, right? I don't think so, right? Okay, so force times distance, definitely there's none of that, okay? It's not an asset, it's not an expenditure, okay? Now, is there any mention of a height? Well, yes, there is. Look at that, right? It starts off at the top of the hill, so we're definitely going to have this to begin with, right? Okay, and that's our height, right? And then the question is it moving to begin with? Well, indeedy it is, right? So we're going to have kinetic energy as well. I don't see any mention of any springs here, so no springs. Okay. And then at the bottom of the hill, we're looking at the bottom of the hill, right? Here it is. Okay. It looks kind of a funny shape too, right? Okay. At the bottom of the hill, I'm going to say the height is 0. So it doesn't have any potential. All it has is kinetic. Okay, now I call this a 2 to 1 because I've solved a lot of these problems. Two things becoming one thing, right? So now all we have to do is just plug our numbers in and solve this, right? Okay, now before we plug the numbers in, do you see that the mass cancels on all of these? Yeah. I call this a roller coaster problem whenever the mass cancels, when it's just potential and kinetic equals potential and kinetic. And the beautiful thing about that is that means the roller coaster's final velocity doesn't depend on the mass of the roller coaster. Okay, so when that's the case, that means your roller coaster is going to work even if it's half full of riders, right? This is a good thing. I'm going to put the mass in there just for fun, and some people like that better. Okay, so we got 250 times 9.81 times 1.75 plus 1/2 mv squared, right? So 1/2 times 250 times 4.5 squared. Okay, and then that equals 1/2 250 v squared, right? Okay, and now we just have to do some good old mathematics, right? Okay, so this whole left side, I'm just going to go 250 times 9.81 times 1.75 plus 0.5, right, times 250 times 4.5 squared. Okay, and apparently I fail at typing things into the calculator. Okay, hold on. Plus 4291 point. Okay. Okay, I get on this side, I get 6823.125. Okay, and then that equals what, 125 v squared, because I took half of 250 as 125, right? Okay, this is a decimal point. Okay, and then I'm going to divide this by 125, and I get 54.585. I square root that, and I get I get that the velocity 7.388 equals my v, which is about 7.4 meters per second. Okay, so that's the general gist. I highly recommend going through all the example problems that we do here. See if you can do them, and then I'll bust them out if you want. So pause, view it, then pause, and then I'll solve it for you.